Let's see. So just let me recall the theorem I'm after. So start with a log canonical pair. Here X is a proper variety. And the underlying assumption is that minus kx plus delta is nef. For example, numerically trivial. Then three things are true. The complexity is non-negative. If c is less than 1, then x is toric. I mean, the other things are true, but let me just say that. And then if gamma is less than 3/2, then x is rational. So let me just recall that the complexity is the dimension of x plus the rank of the span of the components of delta minus the sum of the coefficients. And gamma is very similar. Dimension plus basically the Picard number, let's say sigma, the rank of the class group, well, essentially the rank of the class group minus the sum of the coefficients. Let me give you one more example, just to sort of warm up again. So this is if c is equal to 1, x is not necessarily toric. So, of course, the prediction is it's rational. So you need to start with something that's rational. So let's start with P2 and 3 lines. Of course, that's toric, so that's complexity 0. So the first thing to do is blow up a point, and then if we blow up, oh, I see. Actually, maybe the easiest example is just to blow up 3 points. If you blow up those 3 points, you get the strict transform of the 3 lines, 3 exceptional divisors, and of course that's still toric, so that's still got complexity 0. The Picard number is 3, and then the sum of the coefficients is 6, and the dimension is 2. Picard number is 4, sorry. The sum of the coefficients is 6, dimension is 2. But now the final step is to blow up a point away from a vertex. You'll get an exception divisor, but it's no longer a component of delta. So here the complexity is 1, because when you blow up, the dimension is unchanged, the Picard number goes up, so this increases by 1, and d changes the same. This is the same. So, and then this guy is not toric. See, the key thing is once you've blown up enough, all of these are -1 curves, so they're rigid. But you see, in any decomposition of the canonical divisor with lots of components, this is a component, and yet you see 3 points along it, this, and this, and that's not toric. So, okay, so today, we're going to go over here. Maybe. Okay, so today, explain 3 things: how to reduce to A, x projective q factorial b y sigma equals r or y c equals gamma if c is less than 1. Let's see how to reduce to the case minus kx plus delta is ample. So let me just review. So assuming A plus B plus C, whoops. So assuming these three things, the argument went as follows. What you did is you looked at x, you picked, you looked at relative spec of a direct sum of ample line bundles. So this is an A row bundle, an affine bundle. I mean, it's a vector bundle if you like, I suppose. And then it carries naturally an action of a torus. And then you look at spec of the Cox ring. And then the point is that starting with x delta, you get z theta. So what was that? You pull back the components of delta, then you push them forward. And then this guy is log canonical. And what else? So the complexity is by definition n plus r minus d, but that's the same as n plus rho minus d. X is q factorial, so there's no problem about that. And then m plus rho is exactly the dimension of z, so that's m minus d, so m is the dimension of z. And then there was this lemma, or proposition, I guess. Proposition. So it's a germ of a log canonical pair. If the complexity, which is m minus d, is less than 1, well, so that this is always greater than or equal 0, and if it's less than 1, then z theta is toric or toroidal, or whatever you want to call it. Okay. So let me point out the and then the other thing to realize is that that's enough, because then this is so if c is less than 1, then z is quotient of am, but then you see x is a quotient by a torus, because it's just an AR bundle, a GIT quotient of a torus, and then z, the torus acts on z in the same way, so then x is a GIT quotient of z, but then it's easy to see it's a GIT quotient of affine space by a torus, but a GIT quotient of an affine space by a torus is always a toric variety. So if you assume A, B, and C, then it's easier to see that x is a toric variety if the complexity is less than 1. Okay. Let me just explain, because it's kind of nice, what to do. Okay. So how to prove 3. So sketch of rationality. So the key thing, if gamma is less than 2, the key observation is you can, again, reduce to this case. That's where you need to use the absolute complexity. And then the key thing is that then if the complexity is less than 2, Z is not smooth. It's not a quotient of smooth, but Z is basically is a quotient of it's CdV. That's to say that Z sits inside Cm plus 1, and it's given by some equation Q equals 0, and then a hyperplane a surface section is Duval. So that's the meaning of CdV. It's compound Duval. That means that there's a surface section, a general surface section has Duval singularities. So that's if gamma is less than 2. And of course, Duval singularities come in a bunch of types. There's AN, DN, E6, E7, E8. And then if gamma is less than 3/2, you can show that you always get AN. That's just some reasonably standard computation or log canonical pairs, surface pairs. This is just a surface argument. So AN looks like x squared plus y squared plus z to the n plus dot dot dot. That's what AN means for a surface. And then the dot dot dots are the hyperplane sections. And then the main case, you can change coordinates. So you get x, y. Well, instead of saying dot dot dot, let me just say f of the other variables. x3 dot dot xn. So this might seem kind of strange. You can always change coordinates, right? But you see, don't forget there's an action of a torus. And when I say change coordinates, I mean that the action of the torus, this respects action of torus. So when I say that we're changing coordinates, I want that coordinate change to be equivariant. Okay, but most of the time you can change it in this form. And so Z is xy plus f equals 0. But then you see it's very easy because then Z is equivalent to, I mean, it's given by f divided by y, so it's the graph of a rational function. And so Z is obviously birational to a hyperplane section, and then you take a GM quotient of that, and again that's a toric variety. So Z is birational to a toric variety. In other words, it's rational. I mean X. So Z is birational to a coordinate hyperplane. And then that implies that X is birational to an invariant divisor. But if it's birational to invariant divisor, it's birational to something that's rational. In other words, it's rational. So that's why it's rational. Yeah, so it's kind of it's kind of an interesting argument, right? Because I don't know any other way in general to show that something is rational apart from projection. But the sort of trick here is that you don't project X so much as you project in the Cox ring. You project the you use the Cox ring to project. You project this down to a coordinate hyperplane, then you take a GM, then you take a torus quotient. Yeah. So then the thing is, I don't know how to do. We don't know how to do DN E6 E7 E8 because, of course, it's not so. I mean, it's just harder to manipulate these equations and then understand the torus action. Okay, let's see. Any questions? So I thought it would be interesting just to see exactly where this condition comes, and you sort of see if you want the general case, gamma less than 2, you have to understand these extra cases. Which doesn't seem so bad, but we couldn't see what to do. Okay, so then maybe what I'll do now, the rest of the lecture, I will explain in some sense these 3 steps. Yeah, the key does that. Maybe I'll leave that. Where's this? This. Okay, so first of all, let me do this. Because this is not completely standard. Actually, I'm lying about one thing we can prove. You can see what I'm saying. So let me just give you a basic lemma. So suppose you've got x to y, a birational contraction. Actually, maybe I'm going to regret this, but let me change that to y to x. What does that mean? That pi inverse does not contract any divisors. So it's very natural to see these sorts of maps in the minimal model program, because in the minimal model program you run the minimal model program, so you contract divisors or you'll flip. And that's exactly what happens for such a map. That it won't be everywhere defined because of flips, but you're going from y to x. You run MMP. You only contract divisors. You never extract divisors. So let's suppose that YG is a log pair. So again, by convention, that means that this is just a sum of divisors, sum of prime divisors with coefficient 1. And I let D be the image of G, then 2 things are true. Number 1, if YG is a toric pair, so that means that Y is a toric variety and G is a sum of invariant divisors, then that automatically implies that XD is a toric pair. That's the first thing. And the second thing is that if XD is a toric pair, well, you see, it's not necessarily the case that YG is a toric pair. I just gave you an example. The thing I erased is an example of that. If you keep blowing up, eventually you'll lose the toric condition. But suppose that pi only extracts, or contracts, I suppose, divisors of log discrepancy 0. Oh, so another way it contracts components. No, I actually log discrepancy 0. Okay, sorry, log discrepancy 0 with respect to YG. Then then no, sorry, xd, sorry. Then yg is a toric pair. So you can always go down. If you start with something toric, essentially if you run MMP, you'll only ever get something toric. And vice versa, if you start downstairs, you have something toric, then it must have been toric to begin with if the only divisors extracted by this map have log discrepancy 0. So let me explain that. So 1 is true for many, many different reasons. Perhaps maybe the easiest is just to say that X is proj of some section ring of some line bundle. L is a line bundle. But you see, if Y is toric, then L is given by some invariant divisors with some various coefficients. So then this thing naturally carries the action of a torus, and then this is therefore a toric variety. So hence X is toric. Hence if X is toric. Or you can just say whenever you start with a toric variety and you run MMP, it will remain toric. Okay, for 2, you make the following observation. So we've got the following picture. We've got Y, and we contract down to X. So the first thing you do is you construct another variety Z, and then with a map, let's say, I don't know, what's F. So Z to X extracts every divisor extracted by pi. So the point is that that's possible because you have MMP and well, that's easy because X is toric, so you can always do that. So the key observation is that these divisors are, correspond to toric valuations. They're log discrepancy 0 with respect to XD. XD is a toric pair, so they're toric. So Z is toric. Z is toric. And then what's this map? This map, G, let's say, G is an isomorphism in codimension 1. Right? Because this guy extracts some divisors, this guy extracts divisors, but the same divisors. So these two things are isomorphic in codimension 1. So then the inverse map is a birational contraction. So there's a map the other way, H I suppose, the inverse map. This is a birational contraction. And then this is toric, and so then Y is toric by 1. So now apply 1. It's H. Okay. So that's one rather pretty thing about toric varieties. They're sort of indestructible under running MMP. If you start with something that's toric, run MMP, you get something that's toric. And you can even go the other way if you're a little bit more careful that the only divisors you extract are log discrepancy 0, which essentially means they're components of coefficient 1. Okay. Let's see. Okay, so how to use that? So I'll need the following. Let me prove the following theorem. So I'll call this a DLT modification. But this is a little bit more delicate than usual. Okay, so let's suppose that X is a proper variety. X delta is log canonical. The usual suspects. But now, let's suppose that M is a Neff Q divisor. And this is where I'm cheating a little bit in the statement of my theorem. In applications, M will be minus kx plus delta, or is essentially kx plus delta. So we can't quite prove our result in full generality. We have to assume that delta is a Q divisor. I think for most people, except an expert in the MMP, you really wouldn't care at all. But it bothers me. Anyway, never mind. And then assume that kx plus delta plus m is Neff. So if m, if you know that minus kx plus delta is Neff, you could take m to be minus kx plus delta, then kx plus delta plus m is 0. So obviously that's Neff. So this is going to be okay. Then what's true is that there exists pi from y to x of a rational contraction such that, if I write ky plus gamma, which is ky plus delta tilde plus e, if I write that as kx plus delta, so this, as usual, will be the strict transform of delta. This will be the sum of the exceptionals. This makes sense for rational contractions if you think about it a little bit. And I'll call gamma delta tilde plus e in short. The other thing I want is that n is pi upper star m. Right. I want this to... The thing is that this will be Neff. That's the key thing. That's non-trivial. And then I want y to be projective and q factorial. So I'll explain how to prove that. That's kind of interesting. Okay, let's erase this. So I should point out one sort of so let me point out the key technical thing that's going on here. The thing is that we're not assuming, we're not assuming that x is projective. So we cannot assume that this map is a morphism. Normally when you take a DLT modification, you assume that this guy is, of course. Having just said that, the other thing that's obviously true, y is projective, q factorial, that's the key point, but also this guy is DLT. Otherwise it wouldn't be a DLT modification. But normally for a DLT modification you assume that this map is a morphism. But you're only allowed to really assume that if x is projective. So if you take the classic example of something that's proper but not projective, there's just no way you can assume that this guy, like for example, you can take something like, there are examples of proper varieties which are smooth but not projective. There are two obvious ways to get such a thing. There's an example in Fulton's book of a toric variety, which is a proper variety, but it's smooth but not projective. And the point is that you can flop a curve. So then in that example, it's because x is smooth. So I mean, you take delta and m to be, you basically forget about these. So basically you take x to just kx. So there's no divisors. This map cannot extract any divisors because the only divisors you extract of log discrepancy 0. X is smooth. So the only thing you can possibly do is flop. This is a flop. And then this guy is projective. So if you look at Fulton's example, if you flop any one of the curves, there's 3 obvious curves to flop. If you flop them, you get a projective toric variety. But then this map, there's no way you can take this, so I mean the inverse map is the map I'm looking for. There's no way you can take that map to be a morphism. Or another way of saying it, and if you sort of like these sort of examples, if you take a quintic threefold, a generic quintic threefold, it has a line. It took the general line, it has type -1, -1. You can just do a classic Atiyah flop. If you do a classic Atiyah flop, you're going to get something that's not projective because the Picard number is 1. So if you started with that guy, I think I don't know about that guy if it's a variety or just an algebraic space. But anyway, if you started that guy and then you tried to take a DLT modification, the only thing you could possibly do is flop back to the quintic threefold. And that would be the thing we're looking for. Okay, so there is something interesting going on here. Okay. So with that said, let me explain how you prove this theorem. So as a first approximation, take a log resolution of x, right? So Chow's lemma says that you can after you can blow up and get something projective, then you resolve that, and then you get something with lots of exceptional divisors. I'm going to cheat a lot. I don't want to introduce too many letters. I'm going to call it pi, even though I've overshot the mark. I've gone way too high. And I can write ky plus gamma, which is ky plus delta tilde plus e, sum of all the exceptionals. I can write pi hyper star kx plus delta. So the only problem with this is there'll be another exceptional. There'll be too many exceptional divisors. So there'll be an f. So here f is exceptional. So I'm perfectly happy about my log resolution. It's smooth, projective, therefore q factorial. Everything I put on the left has coefficient 1, so it's log discrepancy 0. But the only problem is that I blew up way too much, and so I need to contract f. So my goal, contract f. And so the basic observation is that, you know, essentially that's in the base locus of some linear system. So you just, if you can sort of contract it because it's in the base locus. So you want to run MMP. So the first thing is, of course, this is true. So let n be pi upper star m, then ky plus gamma plus n is pi upper star kx plus delta plus m plus f. So the same equation is true because I just added the same thing to both sides. And now this is pseudo-effective, and so f is the stable base locus. So f is the stable base locus of ky plus gamma plus n. Great. So if we run MMP, we will contract f. And I don't run MMP over x. I cannot run MMP over x. If I run MMP over x, I will get back to x, maybe. If I started with my Calabi-Yau threefold and I flop the line, quintic, if I try to resolve that and run MMP over X, I will never get back to the quintic threefold, which is where I know I have to end there. So I cannot run MMP over X. That's the delicate thing. But if I contract F, there is, and that's the only. Those are the only divisors I'm ever going to contract. I will get a map that's a rational contraction down to X. Okay. And so now here's the point. Since n is Q Cartier, if I replace it by a multiple, see, it's also Nef as well, and Nef. If I replace it by a multiple, I may assume that if n dot c is less than 2n, then in fact n dot c is equal to 0. Because, you know, if I replace it by a multiple, I can assume it's Cartier. Then I replace it by 2n times that Cartier divisor. Then n dot c, if it's positive, it's at least 2n. So then if it's less than 2n, it must be 0. That's not true if I had an R divisor, because I might get some weird cancelling, and it's like, you know, just isn't true for R Cartier divisors, annoyingly. Okay, now there's one more trick. The other thing is that I'd be okay if we had MMP, but we don't have MMP. We only have MMP with scaling. Okay, I'm going to need this lemma, but I need to erase it something, so I'm going to have to erase it. Okay, so finally, pick a ample Q divisor such that F is the stable base locus, or the support of F, of ky plus gamma plus n plus a. Again, this is the support of F. So if I just perturb by a very small amount of a, I won't change the stable base locus, I mean the support. So that's okay. So now this is of the form ample plus effective. So this is big, and I can run MMP with scaling. So run MMP with scaling of A. So we get array, an extreme array R, and a scalar, I don't know, let's call it T, such that ky plus gamma plus n plus a dot a is less than 0, and yet ky plus gamma plus n plus t times a dot r, so bigger than 1, is equal to 0. That's what it means to run MMP with scaling. So if you look at those two equations, it is therefore obvious that a dot r is positive. It makes sense to say that a divisor is positive, negative, or 0 on any extreme array. So therefore, looking at this equation, this is positive on R, so this must be negative. So ky plus gamma plus n dot r is less than 0. Okay, so then Kawamata says, and then n is Nef. So that tells me that ky plus gamma dot r is less than 0, which is annoying because I've run out of space. Okay, let's just go over here. So Kawamata tells me R is spanned by C rational curve such that ky plus gamma minus dot c is less than 2n. Now you see why I wanted 2n. So I know that this is negative, or this is, I mean, ky plus gamma is negative on c, but not too negative. So n dot c has to be 0, because if n dot c were not 0, it would be bigger than 2n, and then I wouldn't get this equality. So hence n dot c is equal to 0. And now once I know that n dot c is equal to 0, I can make the divisorial contraction flip or Mori fiber space, whatever it is, and keep going. So if I run MMP, if we run MMP, we preserve the property that n is nef. And then that finishes the argument, because I know the MMP terminates. So the whole point, the whole delicate issue is to make sure that every ray that you contract is necessarily n-trivial. And that's delicate because you want three things. You want it to be negative with respect to this, you want it to be 0 with respect to r, and you want the third thing. And normally you can arrange two things to be true, but not the third thing. Okay. So that proves the theorem, and then the theorem, it's not so hard to prove A. So apply theorem to m equals minus kx plus delta. And then if the pullback of this is nef, that implies that minus ky plus gamma is nef. So you can replace x delta by y gamma. Oh, by the way, the complexity is unchanged, right? Because the sum of the coefficients of gamma is precisely the sum of the coefficients of delta plus the number of exception divisors, but that's exactly the relative Picard number. So the complexity, so this is the complexity of x delta is the complexity of y gamma. So if I can prove that y gamma is toric, or y is toric, then I know x is toric by that lemma, and so that does A. Any questions about that? I'm sure the last lecture of a long week you've been paying very close attention. Okay, let's see. So that gives you the DLT modification, and that allows you to reduce the case that x is projective in Q factorial. And I suppose there must be some Diophantine, I mean, I'm hoping there's some Diophantine argument that deals with the case of an R-Carty divisor, but I don't see it at the moment. Okay, so let me state a theorem. X delta is log canonical. Actually, let's say, a DLT. X is projective. Q factorial if minus kx plus delta is ample, sorry. C is less than 1, then components of delta span the class group. I mean, as a vector space, so give it Q coefficients. So in particular, what that says is that it says in exactly that rho is equal to sigma is the Picard number, so C is equal to gamma, which is very, very useful. Okay, let me give you the argument for that. So proof. So it's in induction on R. So the base case, suppose R is equal to 1. Then components of delta span the same ray. Actually, I must confess, there's one thing I don't remember about this argument. It's it's on my computer, which is back in my hotel room. But there's yeah. So they span the same ray in AN minus 1Q, let's say, or in the same space. So if rho is equal to 1. Then we're done. So otherwise I want to get a contradiction. So otherwise we run the kx plus delta MMP. See, that's not quite right. I mean, there's some twist here that I've forgotten. But the point is that this minimal model program is D positive. And that's what I don't remember. But given that that's true, then we're done, because, okay, so if you run MMP and the Picard number is bigger than 1, so we're assuming rho is bigger than 1, so after a sequence of flips, we must get a divisorial contraction or Mori fiber space, which is non-trivial because the Picard number is bigger than 1. We can't. I mean, if we had Picard number 1, we could just get a map to a point, but we can't get that. We must get either a non-trivial Mori fiber space or a divisorial contraction. Let me just draw a picture to show you why that's completely impossible. So, you've got X. Let's suppose it's a divisorial contraction, so the map is birational. And then you've got some exceptional divisor, E, mapping down, I don't know, let's say to a curve. But by assumption, every component of D intersects intersects E. So downstairs, you see lots of components passing through the same point. So if you've got X delta, and so you've got, look at Y gamma, pi lower star of D delta. This is log canonical, it's running MMP. And yet the sum of the coefficients, so every component of gamma passes through the same point. And the sum of the coefficients is greater than n because the complexity is less than 1. But that's a contradiction. That's impossible. There's no way that the components of gamma can all pass through the same point, so there's no way that every component of D was positive for this extremal contraction. There's no way that they could have all met the general fiber of E down to whatever it's mapping down to. So that's a contradiction. It's even easier contradiction if it's a Mori fiber space. You restrict to the general fiber. You just see too many components in that general fiber. Again, it basically just contradicts something we know in dimension n-1. Okay, so that deals with the case when r equals 1. So we must have had Picard number 1, because if we run MMP, we either get divisorial contraction or a Mori fiber space, and we get a contradiction. Okay. So let's erase that. Okay. So r equals 1, that's what I've just done. Otherwise, suppose D1 and D2 are independent. I mean, if r is bigger than 1, there are two components of deltas, let's say D1 and D2 are independent, and so then you can find integers, positive integers, well, integers, doesn't matter, I suppose, integers m1, m2, such that m1 d1 minus m2 d2 and m2 d2 minus m1 d1 are not pseudo-effective. So both the divisor and its negative are not pseudo-effective. And from that, you construct a P1 bundle. So you let y be the projectivization of OX of m1 d1 minus m2 d2, direct sum OX of m2 d2 minus m1 d1. You take those two divisors, that's a P1 bundle. And it's got two obvious sections, E0, E infinity, corresponding to the two obvious projections. That gives me two sections. And then the whole point is that E0 plus E infinity does not move. Because if you restrict, E0 restricted to itself is this guy, which is not effective, and E infinity is the other guy, and it's not effective. So you cannot, I mean, these are negative on themselves, because basically they're just given by those two divisors. So this doesn't move. But you see, X is a Mori dream space. Because I'm assuming I have something Fano, and the BCHM says it's a Mori dream space. In fact, you don't even need this. Really you could say that just assume that X is a Mori dream space. So X is a Mori dream space, so then Y is a Mori dream space. And then Hu-Kiel says that if you give me any divisor, let's say this guy, you can run the D minimal model program. But okay, you've got a divisor which Kodara dimension 0. So after passing to a log terminal model, a D minimal model, that guy should be semi-ample. Well, the only thing you could possibly do is contract these two guys. So there's some map, and it contracts E0, E infinity. So you do a little bit of basic algebra. What's the Picard number of Z? Well, it's the Picard number of Y minus 2, because you contracted two divisors. But the Picard number of Y is 1 plus the Picard number of X, because it's a P1 bundle. So in the end, the Picard number of Z is 1 less than the Picard number of X, and you just do induction. And then you see, you can read off by induction on Z, you know that the components of D generate the class group, and you can just say that therefore E0, E infinity, and then the other guys span the class group, and then it's easy to see that gives it this. So before I go on, let me just ask a question at this point, which I think is interesting, with sort of suggested by this construction. I like this construction. It's something that appeared in Morgan Brown's thesis. Actually, I'd like to claim this, but it's actually not my argument. So let me ask a question though. So question. Suppose X is a rationally corrected variety. Is a rationally corrected variety. Let's say manifold. I don't really care about the singularities. Well, no, let's say projective variety. So obviously that's a very nice thing. And one way to produce rationally connected varieties is to start with Fano manifolds, or in general, KLT Fano. So Shakurov asked, is X birational to a log Fano? And unfortunately the answer is no. There are examples in dimension 4, and there might be an example in dimension 3. This is apparently the work of a student of Shakurov. But there are certainly examples in dimension 4. There are 4-dimensional rationally connected varieties that are not birational to log Fanos. So let me ask a slightly different question. Is X stably birational to a log Fano? You see, because stably birational, what I mean by that is, in other words, so i.e. is X cross some projective space birational to log Fano. You see, because if you go back to that construction I had, I started with X, I replaced it by a P1 bundle. And then I went down to Z. But you see, this is birational to X cross P1. So whatever the Picard number of this had Picard number 1 less. So if you kept going, if you could do this construction for a rationally corrected variety, you'd get down to Picard number 1, and then if you were lucky, it would be log Fano. It would certainly be Fano, but would it be log Fano? Maybe. So it's a suggestion that maybe the answer to this question is yes. Okay, let me, the last 2 minutes, sketch the last bit. I won't say very much about it at all, obviously. So the last bit, so I've explained parts A and B, and we'll now focus on C in 2 minutes. Final step. So consider a ample. Finals. So I look at all those delta prime between 0 and delta, and A ample divisors such that kx plus delta prime plus A is pseudo-effective. So this is a very, very sneaky trick. I really like this trick. Again, it's not really mine, but it's. So you pick delta and A prime such that the numerical dimension is minimal. And then the point is that, so with some argument, if C is less than 1, then you can get numerically trivial. I mean, numerical dimension equals 0. Actually, you can always get the numerical dimension, actually, so minimal, actually this is always less than or equal to C. So it's always less than or equal to round down because it's an integer, right? And then the whole point is that you run MMP. So you start with this guy, which is pseudo-effective. It has a minimal model. And so now you've got Y gamma, the image of this, and the image of A. And then this is if, for example, if it was numerical dimension 0, the ky plus gamma plus b is numerically equivalent, McKernan equivalent to 0, but this guy is big, so this guy is log Fano basically. And then you check the complexity only goes down, so you prove this is toric, and then with some work, then you prove that X is toric, and that finishes the lecture and the argument. Okay.